Hello students, welcome to the EPG Pathshala. I am Vidya Kothekar. I had been at Biophysics Department of All India Institute of Medical Sciences for over 32 years. I had been professor and head of Biotech Bioinformatics in JP Institute of Information Technology, had been director of D.Y. Patil Biotech Bioinformatics Institute at Pune, and my main recognition is I have been teacher of biophysics for more than 40-50 years. Today, we are going to talk about a module on UV-visible spectroscopy, Beer-Lambert Law, Instrumentation. This belongs to the paper Techniques Used in Molecular Biophysics, Part 2. After completing this module, what you should understand that we are going to describe you basic principles of UV-vis absorption. You will know Beer-Lambert law, derivation of Beer-Lambert law, and deviation from this law. We will give you some theory behind UV-vis and near IR spectroscopy, discuss some basic features of UV-vis spectrophotometer and associated practical problems. We like to describe some special instruments which are also based on UV-vis absorption. Atoms and molecules, as you know, undergo electronic transitions in visible and ultraviolet region. And UV-vis, the name, so UV-vis spectroscopy refers to measurement of absorption or reflectance in ultraviolet, visible and near infrared region as a function of wavelength lambda of absorbed or reflected electromagnetic radiation. It is governed by Beer-Lambert law. That's why we are going to study Beer-Lambert law. It has many applications. And you know, because of its applications in the field of medical, biochemical, biophysical, structural, industrial, and various fields, every laboratory, as I know, experimental laboratory everywhere, is always equipped of some UV-vis spectrophotometer. They might change depending on what is the desired output, but you always have one UV-vis spectrophotometer. Basic principle of UV-vis absorption. All spectroscopic techniques are based on absorption or reflection of light. Latter depends on the energy levels within the system. Electron resting at ground state E1, shown in yellow color in the figure, can go to the excited state E2, shown in the red color, with the absorption of photon of frequency nu, described by Planck's law as delta E equal to E2 minus E1 equal to h nu. Let me explain you energy levels and selection rule. Neither energy level nor spectral line are sharp like Dirac's delta function, but both have some widths and also shapes, as shown in the lower side. That upper level also has a distribution, so also has a lower level. Now the transition between these levels can take place only under certain fixed conditions known as selection rules. The spectral lines have usually Gaussian or Lorentzian shape, described by the equation given below the figure on the left hand side, like A equal to B divided by C plus x minus x0 square. So at x equal to x0, the value will be maximum, and as x becomes greater or smaller than x0, the value goes on dropping, and as a result, there will be a line width and line height. The parameters thus of any spectral lines are: first is line multiplicity. How many such peaks are there in a particular transition? Then the line position, that the value of x0. What is the value of x0? Amplitude, shown by the height of the absorption peak, which is shown on the left-hand side rather. The characteristics can be defined in terms of effective bandwidth or line width, which is the width at half the maximum, which can be also taken up as a line shape. And line widths can be related to the detailed structure and dynamics of the system. Beer-Lambert law. The law for absorbance was originally discovered by Pierre Berger in 1729, and later on it was attributed to Johannes Heinrich Lambert. In 1852, August Beer discovered another law, that is the attenuation relationship. But the modern Beer-Lambert law combines both. It correlates absorbance and concentration of the sample thickness. Beer-Lambert law, which was given in 1852. Consider a beam of light with the power I0 and traveling a distance b through an absorbing solution of concentration C. Then the amplitude of the outcoming beam is given by I equal to I0 exp of minus C epsilon L, where L is the path length equal to B, epsilon equal to molar extinction coefficient, and C the concentration of the sample. The number of molecules undergoing a transition, that is Di, can be expressed as minus Kn dl into I, where K is a constant equal to P sigma, where P is the probability that the molecule is met by radiation, and sigma is the scattering cross-section for radiation, N number density, and L is the path length. If we integrate the equation given in the previous slide, we get log of I equal to minus Pn sigma L, which can be also expressed as I equal to I0 exponential to the power minus epsilon Cl, where epsilon is P sigma and N is expressed in terms of concentration C. ODE is defined as log to the base 10 I0 upon I. Substituting the transmittance T, which is equal to I upon I0 multiplied by 100, OD can be given equal to 2 minus log of T, or equal to minus epsilon Cl. Beer-Lambert law, the absorbance A is equal to A multiplied by B multiplied by C. The constant of proportionality is called the absorptivity coefficient. If the concentration is expressed in moles per liter and cell size in centimeter, the absorptivity is called the molar absorptivity or molecular extinction coefficient, and is given a new symbol epsilon. The absorptivity A is wavelength dependent. It depends on absorption coefficient of the sample, scattering losses as light passes through the sample, reflection losses as the light strikes the sail or sail and interference phase, etc. We just show here a simple example of Beer-Lambert law rather. If you have three solutions of concentration 0.001, 0.002 and 0.005 and 0.01, sorry, four solutions, and we know the absorbance by this four concentration 0.21, 0.39, 1.01 to 0.02. Then according to the law it comes out as a straight line, and we can calculate, suppose we have absorbance 1.52, so we can immediately calculate the concentration from this particular curve shown here. There are some limitations to the Beer-Lambert law. Under certain conditions, Beer-Lambert law fails to give a linear relationship between the concentration of analyte and the attenuation. This can be real as fundamental deviation in the law itself. It happens sometimes in some sample. Some chemical reasons, there might be some chemical reactions going in. It can be instrumental also, due to the way in which the attenuation is measured. Validity of Beer-Lambert law depends on following conditions. First, the attenuators must act independent of each other. The attenuating medium must be homogeneous. The attenuating medium must not scatter the radiation, no turbidity, unless it is accounted for. Then incident radiation must consist of parallel rays. They should travel the same path within the sample. The incident radiation should be preferably monochromatic, because the law holds for that particular wavelength only. The incident flux must not influence the atoms or molecules. It should only act as a non-invasive probe, that is, it should not disturb the system, molecular system at all. There are certain basic conditions. The Beer-Lambert law is valid only at low concentration. At high concentration, the average distance between the absorbing molecules becomes small. The charge distribution is affected by proximity of the neighboring molecules. It alters the ability of the molecules to absorb a given wavelength, and then it's not correct. Now, if the analytes dissociate, associate, or react with the solvent to produce product having different absorption spectrum from the analyte, a particular example, like some particular sample having a color 1, then it dissociates, it gets some H atom and some other molecule color 2, then you will get a wrong result. Then truly monochromatic radiation, it comes from a line source, the output many times is not manageable and you do not get a valid Beer-Lambert law, and your measurements turn out to be wrong. Theory of absorption or emission of radiation has direct link with the electronic and molecular energy levels. Analysis of spectral lines and the molecular structure associated with the same is very important and can be studied using UVV spectroscopy. However, major use of UVV spectroscopy is for quantitative determination of components in chemical or biochemical reaction. Atomic spectroscopy. Atomic spectroscopy is the study of absorption or emission of light by atomic electrons. Now, since every element has a unique spectral characteristics, we can use electromagnetic spectra for identifying that atom. It is also possible to use mass spectroscopy to do the same job for discrimination of the elemental composition. However, although mass spectroscopy usually gives you better results, the optical spectroscopy is more common. Why? Because of the cost effectiveness and performance adequate for many routine tasks. What is molecular spectroscopy? Molecular spectroscopy consists of three types: electronic, then vibrational, and third, rotational spectroscopy. One can use quantum mechanical approach for obtaining electronic molecular energy levels using molecular orbital or MO methods such as ab initio, C and duo, complete neglect of differential overlap, I and duo, intermediate neglect of differential overlap, MI and duo, AM1, PM3, and SAM1, etc. I would like to give you a simple example of molecular orbital composed of atomic orbitals characterizing valence electrons in constituent atom. We just assume that there are only one electron, that is 1s electron from each atom. From first atom phi 1 and from second atom phi 2. Then we can write the MO psi I equal to sum over j Cij phi j. For two atomic orbitals, it is very simple. So we get psi s, which is equal to phi I1 phi z2 plus phi I2 phi z1, and psi a equal to phi I1 phi z2 minus phi I2 phi z1. Both are antisymmetric product of the two wave functions. Now in the first case, these two are added, and in the second equation, these are subtracted. So the first are called symmetric bonding orbital, and the second is called antisymmetric bonding orbital. So how these symmetric and antisymmetric or antibonding and bonding orbitals arise? This is because of the constructive and destructive interference. In the first case, or in the first molecular orbital, the two atomic orbitals phi 1s and phi 2s, they have a constructive interference shown in the yellowish color in this figure, and they lower the energy than the energy of the constituent orbitals and stabilize the molecule. That is why these are called bonding orbital. In the case of second molecular orbital, psi a, which we call antibonding orbital, the two atomic orbitals phi 1s and phi 2s, these have destructive interference, and because of this destructive interference, the energy of the combined MO increases, and that is why it is called anti-bonding orbital. So in this figure, which is lower, we show both bonding orbital, anti-bonding orbital, and H1s or phi 1s from one atom and H1s from the second atom. The bonding orbital sigma and anti-bonding orbital have great importance in electronic transition. Let us see how does the overlap between the atomic orbital takes place. This depends on the shapes of the electrons, and latter depends on the principal quantum number, orbital or azimuthal quantum number, and magnetic quantum numbers. Just for example, as shown in the upper figure in the left hand side, if n is equal to 1, then L has to be 0, and then M also has to be 0, and the orbital is spherical. If n is equal to 2, L can be equal to 0 or 1, and L equal to 0 will be a spherical orbital, 2s orbital, and L equal to 1 will have 3 possibilities, M equal to 0, minus 1, plus 1, and we get 3 orbitals, px, py, pz, which are directed in the direction x, y, and z. If we have n equal to 3, then L can be equal to 0, 1, or 2, and we have more possibilities rather. For L equal to 2, we have 5 possibilities of atomic orbitals, and the overlap between these orbitals will depend on the shapes. Energy levels, the sigma orbitals are formed by 2 atomic orbitals or more with m equal to 0, and these are in the direction of the bond. The pi orbitals are formed by overlap in the direction perpendicular to the bond, like by px, py, dxz, dyz, dxy. There are lone pairs, like some electrons, as 2s electrons in NH3, do not participate in bond formation but rotate in the same orbit. Now, the energy levels for such complex molecules, the sigma electrons in those molecules have the lowest energy, and whereas sigma star, that is anti-bonding sigma, has the highest energy. Next to sigma are pi orbitals in the energy level scheme, and lower than the sigma star are pi star, anti-bonding orbital. And in between the pi and pi star, no transition between these energy levels can take place as per the selection rule, delta L equal to 0 or plus and minus 1. UV absorption spectrum is related to the absorption properties of chromophores. For example, C double bond C, C double bond O, and aromatic groups. Only when 2 or more such groups are conjugated, a change in the absorption is observed. Extensive conjugation leads to bathochromic effect. We show here a typical spectrum by 3 different molecules: A, benzene; B, naphthalene; C, anthracene, and you can see the difference in the 3 spectra on the right hand side. Now, how does the environment or local environment affect the spectrum? Wavelength of pi electron transition depends on the size and delocalization of the electron. The peptide pi star electron transition is at 190 nanometer, while in DNA it is around 260 nanometers. In hemoglobin, it is at 400 nanometers. Interaction of solvent has either a stabilizing or a destabilizing effect on the excited state energy level, and it depends on the nature of the chromophore and what transition it is. I want to give you a typical example how a bathochromic effect takes place. For example, E of a particular molecule in cyclohexane is 280 nanometers. In water, the excited state energy level will be reduced due to formation of H bond. And as we know, the normal H bond energy between 1 to 5 kilocal per mole, or we can convert it into kilojoule. And since we are considering only one particular bond, we can divide it by the Avogadro number, and we can get the energy equal to 3.474 into 10 to the power of minus 20 joules. Now, E in cyclohexane is 280 nanometers, or Hc upon lambda can be calculated. And after using H equal to 6.62 10 to the power of minus 34, C equal to 3 into 10 to the power of 8 meters, E in the cyclohexane comes out to be 7.09 10 to the power of minus 19. And thus, we see that is E in water is 6.74, whereas lambda in the water is equal to 6.62, which is equal to 295 nanometers. I just am trying to elaborate the same example, like we show first the bathochromic effect, a chromophore in cyclohexane and a chromophore in water, and the upper energy level, excited state energy level changes. As a result, the wavelength shifts towards the red side. The reverse happens in the case of hypsochromic effect or the blue shift, and we find the change in the wavelength is towards the blue side, and we get a blue shift. There are a number of examples of UV absorption in biomolecules. The sigma star transition around 115 nanometer is far UV range and useful for structural analysis. N sigma star transition is between 150 to 250 nanometers. The pi star transition, which we observe very often, occurs between 200 to 400 nanometer, and N pi star occurs between 400 to 700 nanometer. If the compound doesn't absorb between 200 to 800 nanometers, it means that it doesn't have a benzoid, aldehyde, or a keto group. Amino acid backbone has less than 230 nanometers, side chains greater than 250 nanometers, histidine 210, cysteine 250, tyrosine and tryptophan around 280, nucleic acid around 260 nanometers. These are useful transitions. Now, what instrumentation we need? We need UV-Vis spectrometer, which typically measures intensity of the light passing through the sample, and then it compares the same with the intensity before it has passed the sample. A typical setup consists of, you have to have a source of monochromatic light, a sample holder where you will keep your sample, and an analyzer. Generally, we use light source with the large bandwidth. The most common continuous light sources are tungsten filament between 300 to 2500 nanometer. Deuterium arc lamp, shown in the slide by blue color in the left hand side, is a continuous source which gives you light between 170 to 350 nanometer. Xenon arc lamp gives in the range of 200 to 1200 nanometers. There are also light emitting diodes, LED, in visible region. We just show here schematically an experimental setup. So we have deuterium tungsten lamp on the right hand side. There is a monochromator next to it rather. Then the beam is split into two, a reference beam and a sample beam, or it passes through two chambers. There is a detector. There might be one detector, there can be two detectors also. And ultimately the data is fed for the recording. The detector is usually a photomultiplier tube, a photodiode array, or a charge coupled devices. A single photodiode and photomultiplier tubes are used in scanning monochromators, which filters and passes a single wavelength that lambda reaches to the detector. We'll just see what spectrometers are rather. So spectrophotometer are of two basic different classes rather. They can use a single beam or a double beam. In a single beam instrument, for example, Spectronic 20, all light passes through the sample cell and it has to be removed for measuring reference intensity. In a double beam instrument, light is split into two before it passes through the sample. There can be two detectors for sample and reference, or a beam blocker which blocks one beam at a time, and detector alternates between the two beams. So you save some money in the multiple detectors. The important factor is the sample chamber can be heated and one can do measurements at particular temperature also. Quality of the wavelength selector is very, very important. If you get wrong beam or a diffuse beam or like that, you will get a wrong answer. In liquids, the extinction coefficient usually changes slowly with the wavelength. So, the measurements are usually made at a peak to minimize the error. Stray light, quality of optics like prisms, gratings, polarizers if used, they are very, very important factors for accurate measurements. We just show in this slide a typical experimental setup by Beckman, which is conventionally used in every lab. Let us see now some special applications of UVV spectroscopy. One can measure absorbance at a fixed wavelength. We don't have to change the wavelength, but at different temperature. This is typically done in DNA melting instrument measurements. Like we go on hitting the sample and just measure the absorbance very quickly. One can carry interaction within a cell and measure the kinetics or rate constant of a chemical reaction. One can measure equilibrium constant of a reaction by performing measurements at definite intervals. The spectrophotometer can be attached to a telescope to measure a spectrum emitted by astronomical objects. Astronomical spectroscopy is very, very important field. Also, it is possible to do microspectrophotometry by attaching it to a microscope. So students, let me now summarize what we have learned in this module. First, we describe you some basic features of UVV spectroscopy. Discussed Beer-Lambert law because it is predominantly used in this. Deviation and derivation, importance and limitations from the Beer-Lambert's law. We gave a brief theory, very brief, of atomic and molecular electronic spectroscopy. We introduce you to concepts of bonding and antibonding orbitals, describe basic instrumentation, associated problems with the instrumentation and measurement, and how to solve those problems. We also discussed use of spectrophotometer for some special purpose, spectrophotometers. I thank you very much for your attention.